Thank you very much for the introduction, and welcome everyone to this Layer 1 Solutions workshop. As said, I'm Sergi Delgado, and I'm a postdoc at the University College of London. And today, basically, I'm going to talk to you about fees and dust. This is part of a shared work with some people from the Autonomous University of Barcelona, where I did my PhD, namely Cristina, Guille, and Jordi. Today I'm going to focus basically on Bitcoin and dust, as I said, but if you want to get like a bigger picture of what all the analysis is about and so on, you can check the preprint of the paper online. Otherwise, I would like to start the talk by asking you a question. So what comes to your mind when you think about scalability or scalability issues within blockchain? So if I have to answer this question, what comes to my mind first are, as said, transactions per second. So basically, how much transactions our currency is able to process, and that's like the main issue. But then there's another thing quite important, that is how much data we have to keep in order to run this blockchain, right? For example, with Bitcoin, we are talking around 200 gigs. And this is the blockchain itself, but there are other things that we have to take into account, and this is basically what we are going to talk about today. So, since we're going to talk about dust, we need to talk about fees first. And I'm more than sure that most of you will already know about this, so I'm not going to waste a lot of time with this. So basically, what are fees? Fees are, in transactions, are the difference between the sum of all inputs and all outputs. And they could be collected by miners when they are including the transactions into the new mined blocks, right? But during the meantime, all those transactions will sit in the mempool of the nodes waiting to be included. So basically, if there are more transactions in the mempool than the ones that a block can fit, who will decide the order of those of the inclusion of those transactions? So as you know, these are miners, and therefore fees can be seen as an incentive for miners to include our transactions first instead of other ones, right? Then, since the block size is limited, as we said, the better the fee, the more likely your transaction to be included. But here comes a question again. Does better here means higher? And as we will see during this talk, the actual answer to this question is not always. So then, what do we need in order to calculate the fees of a transaction? There's basically two factors that matters here. The first one is the transaction size. So basically, the bigger the size, the bigger the fees that you will need to pay. And then we have the fee rate at the moment of creating the transaction. So talking about the transaction size, here we have a high-level representation of a transaction. Don't worry, I mean, we are going to go back to this later, so you don't need to learn everything about it. But what I would like you to check here for now is that there are some fixed size parameters that are always going to be the same size. And there are others that will depend on the transaction we are creating. So depending on the type of the transaction we create, the size will be different. Then regarding the fee rate, this is also a highly variable factor and depends on the transaction by lock, which is the number of transactions that are sitting in the mempool in order to be included. So basically, what we need to do, what we need to know here is that the two factors that matters when we are talking about fees are highly variable and will depend on the state of the network. So at this point, you may think, all right, but what will happen if the value of a transaction is actually really, really low compared to the size of it? So the size is high, the value is low. Or even what will happen if the fees that we need to pay for a transaction at a certain point are really, really high. So here is where dust comes into play. But what is dust? OK, so dust is a definition coined by the Bitcoin Core, as far as I know. And it is computed in terms of output instead of in terms of transactions. So basically, what the definition says is that an output will be seen as dust if the value the output is holding it's lower than the fees you need to pay in order to spend that output, right? Therefore, again, dust will depend a lot on the state of the network. But you may ask here, all right, if I have a Dust transaction, or if I have a transaction without Dust outputs, does it mean that this transaction is invalid? Well, there's a lot of misunderstanding here, a lot of misconception. And you may not be the only one asking these kind of things. Actually, the answer to this question is no. That's not how it is. And how it works is that when a transaction is seen as Dust, so if a node sees a transaction being Dust, what they will do will be not to propagate those transactions. Basically, Bitcoin Core node, so we are talking about a specific implementation of a node, right? But this doesn't mean that the transaction is invalid. If a miner receives this transaction and he decides to include this transaction in a block, that will be completely good, right? There's no problem with it. The block won't be invalid. So the thing is that there's a quite difference between what are relay rules and what are consensus rules. However, they were like halfway right, because the actual suspect for Dust are really low-value outputs. So, at this point that we know what are fees and what is Dust, can we flag uneconomical outputs? The answer is yes, we can. And we can do it by analyzing the UTXO set. So the UTXO set is the set of all UTXOs, as the name suggests, right? And UTXO stands for unspent transaction output. And if you were wondering why I've been talking about outputs all along, that's the reason why. So basically, every single Bitcoin full node or Bitcoin Core node needs to store this set. Doesn't matter if they are running, if they are running a full node, right? But it doesn't matter if it's a prune node or it's an actual full node. They have to have it. And every UTXO will be an entry in the set, which means that the more UTXOs, the bigger is the set, right? Quite straightforward. Then the thing here, one of the really important things to know is that the value hasn't anything to do with the size. So the bigger the value doesn't imply the bigger the size. Actually, in general terms, the bigger the script the output is holding, the bigger the size of the entry, and therefore the bigger the set, right? So knowing this, we can analyze the set, and by doing so, we can mark which outputs will be uneconomical and which ones will be worth spending. And the other positive thing here is that since there are a lot of Bitcoin forks in terms of software, by sticking to the representation of the UTXO set followed by the core, we can use the same tool to analyze all of them, right? So basically, one tool to analyze them all. And so we did. We created a tool called Status, which stands for Statistical Analysis Tool for the UTXO set. It's an open source tool. You can find it on GitHub if you like. It's coded in Python, and it provides an easy way to access the code and analyze the data from the set. Right. For those of you who are coming to the workshop later, we will be using the tool and playing around with some fun facts of it. So you can download it now if you want. Otherwise, we can talk about it later. So all right, we have a tool. We have our definition. So what are the questions we're trying to answer here? The first one is how many UTXOs are actually worth spending, as I said. And the other one, an important one, is how much space is wasted by outputs that are not worth it, right? So how much space every single node is wasting just because they have to store this kind of outputs. And we are going to use two metrics here. The first one we have already introduced it a little bit, which is Dust. And the other one will be unprofitability. Both are metrics that are defined in terms of output, so basically the thing I said, depending on the value of the output and what you need to pay, but they are computed using a different approach. All right, so here comes math. It's going to be quick and it's going to be fairly easy, so don't panic, please. All right, so in order to compute Dust, the core, what they do, they use the output we are checking, and they take that into account, and they also use an input from a pay-to-public key hash transaction, right? So basically, what this says is that an output could be seen as Dust if the value that the output is holding is lower than the fee rate times the input, that's the 41 plus 107, and then also the output size, right? And then we have here one parameter that defines if the input is SegWit, then we have some discounts here, like 1/4 and so on, right? So we also have coined the definition, which is the unprofitable output definition, and it's similar but different. We here are only using the input that will spend the output we are checking. So basically, since the output are sitting in the UTXO set, and we need to create an input for every kind of output, what for us actually matter are the input we are going to create. And in order to do so, we are checking more or less the same. So if the output value is lower than the feed rate times the predicted input, then we will see that this input is unprofitable. Otherwise, we will say that it's not, right? And again, we have the SegWit discounting here. So as you may see here, we need a way of predicting this input, right? And how can we do it? Well, if you recall the transaction structure I was talking about before, we have some fixed size parameters and we have some variable ones. The fixed ones, since we are only looking at the input here, so only this part here, right? We have the out point, which counts previous transaction ID at the output, and then the end sequence. All those are going to be 40 bytes. Doesn't matter the type of input we're creating. And then we have the variable size, which will account for the input script and the size of the script. And this will highly depend on the type of input we are creating. So there are two approaches here. The first one talks about non-SegWit inputs, and the other one about SegWit. If we check the non-SegWit, the traditional ones, we have pay-to-public key, in which we have to take into account a data push, which is 1 byte, and then the signature that can be either 71 or between 71 and 73 bytes long. Then we have pay-to-public key hash. Here we have two data pushes, the signature, again, 71 to 73, and then we have the public key, which can be either compressed or uncompressed. If it's compressed, it will be 33 bytes. If it's uncompressed, 65. Pay-to-multisig, more or less the same. Op0, then we have the push and the signature, and times the number of signatures we have here, right? So if we have 3, this will be multiplied by 3, and so on. And finally, we have pay-to-script hash. And here, well, here we have an issue. Because when we check pay-to-script hash scripts, we don't know exactly what's going on in there. We know what's the hash of the script that we need to pay to, but we don't know exactly what was the script that created exactly this hash, right? So there's no way we can know how long is going to be the input that spends that output. And regarding to SegWit, this is quite similar. We have the pay-to-Windows public key hash, in which, again, we have a push, the signature, and a public key. In this case, public key have to be always compressed. And regarding pay-to-Windows script hash, exactly the same as with pay-to-script hash, right? So, and again, sorry, we have the discount here. Cool. So, seeing this, we decided to split the non-profitable metric in two. The first one will account for a lower bound. So basically, what we will do will be to take the minimum size of signatures, that will be 71. And then for the data we don't know, we will simply don't count it. So basically, for pay-to-script hash scripts, what we will do will be only count for the fixed part and count the variable part as 0. And then we will have a different one, which is like definitely better in this case, because we will try to predict as good as possible how this how long this size is going to be, how big the size is going to be. Basically, we will take 72 bytes here because it's the most likely ECDCA signature length. And for the data we don't know, we will take data from the blockchain. Basically, we have to use BlockSci here to gather all the information we could from the blockchain, and then compute the average size of public keys and redeem scripts depending on the block height we are talking about. So here you can see some charts from the size of the public keys. We can see how at the beginning it was like all compressed. There was not uncompressed implementation of the keys, and then it goes down. So basically what we do when we are analyzing one output, we check the height of the block it was included, and then we check what was the average of that size and count that part. And then for redeem scripts, more or less the same. It's far from fixed, so we just check the block the block height and then take the average of it. All right, so we have all the definitions, all the methods, every single thing, so it's the right time to talk about results. Right. In this chart, we can see the three metrics. Dust in dotted blue, we have a non-profitable estimation in green, and then the lower bound in dotted orange. And here, so basically, what we have in the axis are the portions of UTXOs that are dust or non-profitable, and then in the X one, we have the fee rate, right? So we've tried to use a quite wide fee range in order to see what will happen depending on which fee it's used at the current time. So this data is from around February this year when we performed the analysis, and we can see how for around 50% of the UTXOs in the set, so around here 0.5, if we go to the X-axis, we are around 115, sorry. What this means is that for around 115 satoshis per byte onwards, more than the 50% of the UTXOs are dust or non-profitable. And if we check to which value this accounts for, so how many bitcoins in circulation at that time we were talking about in this 50%, if we again go to 115 more or less, we will see that this is really a tiny, tiny amount. So it's around 0.015% of the total value of the coin. So it's almost nothing. So then what are the implications of this? The implications are that more or less the half of the UTXOs in the set are dust for around 100, 125 satoshis per byte, which are around 3 million UTXOs. In terms of size, we are talking about 1.7 gigs of data, which are dust for this range. And in terms of value, we are talking on almost nothing. So basically, the whole picture in here is that almost nothing in value is being stored occupying half of the size of the UTXO set, right? And don't get me wrong, this is a lot of money. We're talking about 252K Bitcoin. So I mean, in terms of money, it's money, but in terms of every single Bitcoin in circulation at the time, it's not that much. All right, so if you think that, all right, that was just one snapshot, right? So this could be better. It could have been just like one thing. The bad news here is that it's not. If we check the evolution, that has been going on for quite a while. And the thing is that now we are getting to a point in which this can actually be a problem. It could be worse. Actually, if we check the 400K snapshot, which is this one, we can see that there was like way more dust in the lower bounds, which is really, really bad, and that was corrected. So, I mean, at that point, all right, we are not as bad as we can be. But this could be really, really, really worse. And if you don't believe me, one of the analyses we have also performed has been done in Litecoin. And Litecoin is definitely the extreme case, because there, around 75% of the UTXOs in the UTXO set are dust for around 1 Litoshi per byte. And this is because around 50% of the UTXOs in the set are actually worth exactly 1 Litoshi. And this is due to an attack, a spam attack that happened around 2011, 2012. So before you go crazy on Twitter, like blaming Charlie Lee about like, yeah, what's happening with Litecoin, what's that thing, and so on, we were talking about this at this Halib Bitcoin at the beginning of this month, and I think he did a quite cool thing, reaching awareness about it to the community of Litecoin and asking their opinion about what they should do. So in my opinion, the results are quite even. There's not that many people who actually respond to the poll, at least, but at least he talk about it. I mean, it's like, this has happened, we can do things if you like, so what's your opinion, right? I don't think they will like get rid of this, because that will imply all kinds of problems in terms of censorship and so on, but at least, I mean, they talk about it. Okay, so time for conclusions. We have seen that a fairly big percentage of the UTXO is dust for different currencies. This is a problem since the current implementation of the UTXO set can grow unbounded, so it could be as big as possible. The bigger the set, the less suitable it is for nodes to run in optimal conditions. So for example, think that when miners are trying to verify transactions, they hold the UTXO set in RAM because it's way faster to check all the UTXOs if you have it in RAM. If you have to waste 1.723 gigs of RAM storing things that are not likely to be spent, you have a problem, right? And then finally, spam attacks can happen in order to make the set grow. If we think about Bitcoin here, I mean, it will take a lot of money to do it, but it could happen. It just only takes someone with enough incentives and willing to spend the money to make it grow. All right, so solutions of this. There's a few I know. The first one I heard about was by Peter Todd called TXO commitments, and it's been floating around for a while, even though I think it hasn't been implemented in any coin yet. There's also the high-performance Merkle set by Bram Cohen, which I think that it's been implemented in Chia Coin, but I'm not completely sure. Most recently, we have heard about RSA accumulators by Benedict Bunz and Dan Bonnet. I haven't seen the paper yet because they talk about this on Scaling Bitcoin at the beginning of the month. And I think the paper is not available yet, but I'm definitely looking forward checking it. And also in Scaling Bitcoin, Touch talk about UTXO accumulators, which was a similar construction, but again, I just heard it talk. I haven't seen any paper yet. There may be some more, I don't know. I mean, if I'm missing someone and you know about it, please tell me. I will definitely like it. All right, and to conclude, what can we do about it? So what can we models do about these kind of things, right? So there are two things I think we can do. The first one is output consolidation when the feeders are low, like now. So if you can know what are your outputs, and there are outputs that are likely to be dust in the near future, if the fees go up, you can do it. And then, please, if you're from an exchange and you're moving a lot of Bitcoins, use a good coin selection algorithm in order to avoid generating more dust. All right. So that will be all for me. Don't forget to check the paper if you're interested and you would like to have a bigger idea of what this is. Reach me on Twitter if you have any questions that I'm not able to solve now. And thank you very much for your attention.
Great. Thank you, Sergi. That was really interesting. So we're going to have some time for questions now. Belle here has a microphone, so if you could put up your hand if you'd like to ask a question. Maybe I'll start. So it sounds to me like there's then these uneconomic transactions that are just part of the UTXO data set, filling up space, wasting it, potentially. What do you think we should do about it? Should we delete them? Can we delete them?
Not really. I mean, that's actually part of what Charlie Lee asked in his post. Sorry. And I think that the actual approach will be looking to the solutions like Benedict is looking for, or Taj is looking for. Like, try to have an accumulated state of the UTXO set that nodes can store, but they don't need to store like the whole thing, and they can verify every single thing just with proofs and the accumulated state, right? The thing is that if you try just to delete it, you're how to say it? You're censoring some outputs. So the bigger idea here is not your Bitcoin or not your Litecoin, not your keys, not your Litecoin, right? So if it's not yours and it's in there, you should keep it. That's how it works. If you don't do it, if you take it out, then, I mean, it was not yours, so why are you like putting your hands in something that is not yours, right? That's why I think that they are not going to change it, at least here, like just throw it out, because the implications for me are way worse than just waste some space.
Great, that makes a lot of sense. There's a question here, Patrick.
Yeah, so I remember Coinbase had this problem. They had something like 1.5 million outputs worth 265 Bitcoin, which was really criticized in the community. But there's actually like a privacy trade-off. So the idea is that if I have 1.5 million outputs, you don't know they belong to me. I can bind them into a single output, and now you can say they all belong to the same person. So do accumulators help with that in terms of privacy, or?
I really don't know, since, I mean, Benedict was talking about like the accumulators and so on, and he talked about the construction, and that could be applied to the current state of the UTXO set, but I don't think he talked about like the implication of this. Okay. I don't know exactly the construction. I mean, it's something I should read in order to know if
finding out if it's sort of user initiated or versus initiated by the network. Because that would obviously help with the privacy if it was done by the network.
Yeah, but I recall like the spam, well, the thing you said with Litecoin, that was actually in one of the higher peaks of the fees. So fees were really, really high at that time, and they were like having a lot of UTXOs that everyone has to store. So they couldn't get rid of them because they have handled the coin selection in a bad way, and they were like generating a lot of dust. So that's why you shouldn't. Yeah.
Hello. So this model is dependent on a UTXO-based model, but is it similar in a balanced account-based model like Ethereum?
No, not really, because you don't need to hold the UTXOs in that part. I mean, there's other problems in there, like having to store or keep track of the accounts, the balances of accounts that are not used, but it's completely different in this sense, because there's no dust in that case. There's no since dust is paid in terms of the output you're using, what can happen is that when you use one of the outputs, it could be you need to pay like more for spending that what this output is giving to you in the transaction, right? So then you're in a point in which you keep adding money, but you need to pay more money, and this doesn't happen in Ethereum, fortunately. So yeah, it's basically a UTXO set model.
Hey, I just wanted to ask that, is there any information whether these UTXOs are abandoned or just infeasible to spend?
That's an actually really good question. The thing is that you don't know, because just by checking the UTXOs, you can actually check if that address has been used recently. But if you follow like every single recommendation by Bitcoin, you shouldn't reuse addresses, right? So there could be like a lot of UTXOs that are in the set sitting there for a long time, but you don't know if those keys has been lost. If not, you have no information about it. So I mean, if the keys has been reused recently, you can know that they are. I mean, someone had them. But if not, maybe they are just holding. You know.